Hello everyone, welcome back. Let's dive in. This is one of my favorite topics. I think it's really interesting. It ties a bunch of stuff together. I really wish we could be doing this together for so many reasons, but we can't, so let's dive in. All right, this is called the standard normal. Last time we were looking at the normal distribution. This is the standard normal. I would include that title and really emphasize the word standard. We're standardizing some stuff to help comparisons. As always, let's start off with a recent review to kind of get some ideas going. Go ahead and pause the screen and give these a shot. Okay, hopefully you had a chance to do that. Let's go over these. So without a calculator, without a GDC, if the mean weight is 330 and our standard deviation is 8, so here we're looking at the probability of it being less than or equal to 330. Well, notice that's the mean, so the probability of some outcome of one of these drinks that we weigh being less than our mean, so that's right here. We're asking for the probability of it being less, so we add all those up, and you're just going to get 0.5. You're going to get half of the distribution here. Next one, probability being between 322. Again, if this is 330, our mean, and our standard deviation is 8 here, then I go down one standard deviation. I know this is 322. And now up to 346, well, the first one would be 338. The second one, go another 8, and you get 346. So I'm adding together these three sections here, and that's about 0.82. Next one, the probability of x being greater than or equal to 338. Remember, the probability of it being greater than or equal to or just greater than for continuous variables is the same. Again, that's just a property of continuous variables because the probability of it equaling any exact value is essentially 0. Okay, so 338 is here and it's wanting greater than, so we add together those three sections, and if you want even just all that, and you get about as you see down here, 0.159, somewhere around there. All right, let's practice using our calculators now. So what this tells us is there's some distribution, some variable is distributed normally with this mean and this standard deviation. Okay, so let's go ahead and go to our calculators. Let me pull over so you guys can see this. Okay, so from our y equals, I'm going to go vars. I'm looking for the normal PDF. There's my normal PDF. And as I said over here, x, 5, and 1.2. So we have x, comma 5, comma 1.2. Okay, now let's talk about setting the window right. Setting the window right is going to be essential for this to work out. So I'm going to click window here. For my x's, if my mean is 5, my standard deviation is 1.2, maybe 0 to 10 is going to be okay. You just want to set your window several standard deviations above, like 5 standard deviations above. So I'm actually going to go 0 to 12. We'll go 0, 12. Now our y's. Y's, remember, the vertical axis for all of these is a probability. Probabilities are never greater than 1. So, and we're not going to have negative probabilities. So I'm going to set my y min to 0, my y max to 1, and then fingers crossed we get a nice graph here. Okay, awesome. That's a nice bell curve. Okay, the skill we're working on now is using this to find the probability. So here we're asked to find the probability x is less than 4. Well, notice 4 doesn't fall nice on one of these standard deviations like in the previous question. If you have to do this without a calculator, you need these intervals to be nice multiples of your standard deviation and your mean. With a calculator, we're free from that. We can do any value within that range. So if I'm going to try and find the probability x is less than or equal to 4, well, I'm going to go second calc here, integrate, and what's a lower bound? Now for your lower bound, you can use 0 or several standard deviations below. You can put in a negative value. I'm just going to put in 0 for now. 0, enter. Our upper bound is 4. And there it shades us and tells us the probability of that is about 0.002. Great, let's do the next one. Now just remember, if you want that shading to go away, you can go in and deselect your function and reselect the function, which causes it to regraph. Regraphing it resets the shading. Okay, now we're just going to integrate between 4.5 and 8. So second calc, integrate between 4.5 and 8. And there, again, this is a probability density curve. The area under the curve between two values tells us the probability density curves. So here, in doing that, we get 0.655. Next, let's do the last one. Again, I'm going to tell it to regraph this function so it erases the shading. I just put the cursor over the equal sign, hit enter, enter, turn it off, turn it on. Now this is the very last one. We want greater than 5.5, second calc. 7, my lower bound is 5.5. My upper bound is just something big. I know I set my window to 12, so I'm just going to go to the max my window, 12. And there it shades the curve for us, and we get a probability of 0.338. Okay, let's continue onward. I would have liked to go over the assignment, go over questions there. Okay, so last time we did the normal distribution, which is just these nice bell curve. Then we started looking at how to do these with our calculators for values that aren't right nicely on the standard deviations. Now we're looking at something called the z-distribution. Real quick recap. Remember, this is the function, this awesome thing. You could actually graph this. This is what your calculator is doing. A second ago we did in the warm-up when we typed in that normal PDF. When we have normal PDF, this is essentially doing this. It's just condensed and much nicer, of course. So just a quick recap. So the variable x is distributed normally with some mean and some variance here. And it's telling us if you want to find the probability of your variable being within some window, just integrate on that domain. Okay. Quick reminders. Remember, this is all integration. This is all area under the curve. For continuous variables, we have these probability density curves, and we find the area under the curve to find whatever our probability is that we care about. And now, this idea is going to seem weird at first, maybe. Remember, for every situation, whether we're measuring lima beans, cats, dogs, human hairs, for every distribution, there's a unique mean, there's a unique standard deviation. They're all unique. So really, there are infinitely many possible functions that could satisfy this, and that kind of gives us the need for what today is. Oh, and the total area under the curve for every single function ever, well, the total area, because these are all probability curves, has to equal 1. Okay, let's dive into what's called the standard normal distribution. Again, emphasize the word standard. We're standardizing it. Okay, here's the main slide, and I just wish we had so much time for you guys to do this individually. I mean, do this as groups. I would have us go to the boards. We cannot. Pause, take a moment, really think on this. This is crucially important and the meat of today's entire idea. So don't just be whimsical about it. Really put some thought into this. Pause the video now. Okay, hopefully you had a chance to pause the video again. This is a huge idea. How do we compare different scores with different means, different standard deviations? These are all different situations here, all different distributions. How do we possibly compare? Obviously, a score of 81 is really high, but with a higher mean and a high-ish standard deviation, what does that really mean? So usually in a class, people start to figure this out, but here's what we're going to be looking at. We're going to be looking at, well, how far is her score from the mean? How far is that? And then divide by the standard deviation. So again, how far is the score? So 81 to 60, that's really far from the mean. That's 21 points. But now if it's a huge standard deviation, maybe 21 points doesn't mean all that much. So we want to take into account the standard deviation. So here's what I would hope people would land on. Let me go back over here, show you guys some work. Okay, so for the English class, if you take the score minus the mean, divide by the standard deviation, you get that. And we repeat that for all of these. Take the score minus the mean, so you get the distance between those two, divide by the standard deviation, you get that. And we continue on score minus mean, divided by standard deviation. That's a huge standard deviation. 68 minus 50 divided by 20, you get 0.9, and same for math. So from looking at this, if we were to go back to the question of ranking her scores, it looks like she actually scored best, the most significant on her Mandarin test because she's the most number of standard deviations above the mean. Her second best test was actually math here, it looks like. She scored 2.267 standard deviations above the mean. While in biology, she still scored really well in biology, above the mean, which is fantastic. Technically, that's her lowest rank, because when we divide by this huge standard deviation of 20, we get 0.9. So she's only 0.9 standard deviations above the mean. This is a huge idea. If that made sense, great. If not, maybe rewatch that. Maybe just pause and rewatch that section. Okay, let's continue. What we just did here is called the normalizing or Z standardizing. Okay, so what this is, so the standard normal distribution or the Z distribution, this is a huge equation. Write this down, make it tremendously obvious. Circle it, highlight it. This is the big idea for this idea. All right, the Z-score tells us how many standard deviations a score is from the mean. I would also record that. That is this in a nutshell. And if you can remember that throughout your math career, things are going to be easier for you. Okay, so again, how many standard deviations from the mean are we? Now, for most of history, people didn't have these fancy graphing calculators that do a lot of this for them. In your college statistics class, you might have to do this without a calculator. So I just want to plant the seed, but you will not be expected to do this in this class. Okay, so for data sets, and actually this is what the IB guys had to do before 2014, you would be given some data set, something like these, convert all of these to z-scores with this equation here, and then you'd go look in this table to see what does that z-score mean. So just as an example, let's say we have a z-score of negative 2.9. Let me just say negative 0.0. Let me go this one actually. Negative 2.19. So what that means, you go find to the tens place here, go all the way over, and here's telling us the probability of that is that value. Let me go to this next slide. Let's say we do all those calculations and do the z-score of exactly 1. So a z-score of exactly 1, you go to this table, 1.00. So the probability, and here it shows us on this curve what this is, the probability of something being below this score. So let's go back to the tests. Let's say she was exactly 1 standard deviation above the mean. The probability of that happening is, well, this section here, this 34%, plus this 50% here. And that's how we get back to this probability, 0.8413. Most likely, if you take a college statistics course, you will be seeing these tables. Again, these tables, let's imagine a score of 0.13. So a z-score of 0.13, 0.13. So the probability of something being below that score is that. Try one more. Why don't you try real quick, 0.62. Okay, so 0.62, the probability of something being less than 0.62. We go 0.62. The probability of something being less than 0.62 standard deviations from the mean, or this whole section, is 0.732. Okay, let's continue onward. I'm seeing my time's running out, so I'm going to do this lesson in 2 parts. I'm going to end this video here, check part 2 for the second part of the lesson.